So once again, good afternoon. Thank you for attending this class. Na leo tutaanza topic mpya ambayo inaitwa Electrostatics. As you heard from the president last week, kumefunguliwa, so be prepared for kurudi shule. We will be going back to school, but once we go back to school, we might not be able to go through whatever we have been teaching, what I've been teaching. Labda tutafanya revision kidogo before we begin our main exam. So continue revising, continue reading for the units ambazo mmekuwa mkisoma online, so that when you go back to school, usikuwa disadvantaged when you are told that you have 2, 3, 4 weeks to the end of term exam. Now, when we talk about electrostatics, we are essentially talking about the study of, we're talking about the study of static charges. Static charges ni zile ambazo hazisongi. We are studying the charges and how they behave. Kwa mfano, when you take a ruler, you rub your hair with it, you'll find that hair will be attracted to the ruler because you have static charges on which are induced on that ruler. Remember, I'm sure you're familiar with magnetism, how magnets work, the attraction and the repulsion of magnets. Now, the field of electrostatics will be touching on some of those familiar topics, attraction, repulsion. But now we're going to be talking about magnetism, we'll be talking about charges. Remember that electrons, any material has ions. We have positively charged particles, and we have negatively charged particles, and we also have neutral particles within a substance. The negatively charged the electrons, the positively charged are the protons, and the neutral are the neutrons. Now, we will begin by mentioning a few terms that we will find when we talk about electrostatics. And the first thing I want us to mention is the electric field, electrostatic field. Now, remember, when you pass a current through a substance, the current will be carried by negatively charged particles. Those are the electrons. Okay? Now, this is because we have an electric field. That force that allows those electrons to move in that conductor is what we term an electric field. Now, for example, in this figure I have here, we have a plate, two plates A and B. We have the first plate, which is a positively charged plate, and we have another plate which is negatively charged. Now, what happens when I place an electron? If I place an electron in this field, remember an electron is a negatively charged ion, you will find that the electron will be repulsed. It will be repelled by the negative plate B, and it will be attracted towards the positive plate A. And the same thing, if I place a positive charged particle or ion in this field, you'll find that the positive plate A will repel that positive charged particle, and the negative plate B will attract it. Are we together? Now, the region in this plate where that electric charge experiences a force, that force is what we call electric field, that region where there is a force. Now, when we have a charged ion, in this case this is a positively charged particle, you'll find that the electric field radiates from the center of that particle. When you bring two charged particles, one with positively charged and another negatively charged, you'll find that the electric field behaves like this, come a magnet, such that these electric lines, which are known as flux, F-U-L-X, electric flux, those lines of the electric field will be emanating from the positively charged particle to the negatively charged particle. Sawa sawa, tuko pamoja? Okay. Now the direction of this line is from, of this flux, of this field is from the positively charged particle to the negatively charged particle. Remember that the field is that force acting on the electron, that charged particle within that field. Yeah? So that force will be emanating from the positive side to the negative side. Now there's in this diagram, the second one, you'll find that this field is not uniform. Yeah? Reason. As I was saying, this field is not uniform. The reason is, once you place a charge in an electric field, you'll find that the force, the force acting on that charged particle will be acting at 90 degrees to that. Let me present something else so that we can understand what I am saying. Now, I want us to look at this diagram over here. Now, we have the positively charged particle and the negatively charged particle. We place a positively charged particle we place a positively charged particle on that positively charged particle Q1. Now, what happens? Yeah? This particle that is positively charged will be repelled by Q1. Now, the force that is acting, now this force 1, F1, is that force of repulsion, and F2 is the force of attraction by this Q2, because it is a negative charge particle. Now, the force of repulsion will be greater than the force of repulsion. Okay? This is because of the distance between that charged, positively charged ion and that Q1, because it is positive. Utaona that the distance between this particle, which is positively charged, is nearer to Q1 than it is to Q2. Therefore, the force of repulsion, F1, is greater than the force of attraction. But when this particle moves within the field, you'll find that this force will start to vary. This F1 will reduce as this particle moves away from the positively charged Q1. And as it goes towards the negatively charged Q1, it is being attracted. Therefore, the force F2 will increase. But something I want you to notice, this resultant force, the resultant force will not change. Because these two forces, F2 and F1, zitakuwa zina change. But the force that will be acting on that, the resultant force acting on that particle will be constant. So when we trace these points as it moves to in that field, utapata kwamba this flux, ama the lines of the electric field are not equal. You'll find that those that are when you plot many points within that field, utapata that this this electric field is not equal. Some places will be stronger than the other. Now, we can be able to make that field uniform. And how do we do this? We can use two parallel plates. We can use two parallel plates. In these parallel plates, you'll find that when they are close together, this field upper katikati will be uniform. And this is denoted by the straight lines that are parallel to each other, but haitakuwa uniform kila mahali. We'll have at the ends, these ends, you'll have an uniform electric field, and this is known as the fringing effect. Fringing effect. But we can make the uniform of an electric field, the field of the electric field uniform by using parallel plates, and this is where the idea of a capacitor comes from. A capacitor is just two plates that have a dielectric, an insulating material in between, and we will see how a capacitor works in a bit. Now let us talk about another term known as electric field strength. We have seen that, now there's something I forgot to mention in this. Now these lines, the closer the lines they are to each other, the stronger the field, the electric field. It just indicates the field strength. Now when you're drawing these lines, you have to remember that these lines are, the electric field is a vector quantity, so you have to indicate the direction. It has a magnitude and it also has a direction also. So that means as you draw these lines, you have to indicate their direction. Now there is something I need to mention that I haven't indicated in this slide. Now the force of attraction and repulsion between two electrically charged bodies is proportional to the magnitude of their charges. We had talked about charge in the beginning of our classes when we were talking about electrical quantities. Kuna mtu anaweza kumbuka what charge means? Is there someone who has an idea of what charge meant when we are talking about electrical quantities? Now, charge is that property of a material to be, when you place it in an electric field, a force acts on it. That's what we call charge. We had mentioned it a few times before. But now I'm saying the force of attraction and repulsion. Remember when you place, let's say, a charged body next to an uncharged body. Ukiweka a body that is charged next to a body that is not charged, it will induce a negative, the opposite charge on that uncharged body. For example, if I have my ruler and it is positively charged, and then I bring it close to my skin, then my skin will become negatively charged. Now the force of attraction and repulsion between the ruler and my skin will depend, will be proportional to the magnitude of their charges, and inversely proportional to the square of that distance. Now what do I mean by this? The force of that repulsion, the force of attraction between two charged bodies will depend on the charge between those two bodies. Will be proportional. Will be proportional to, let me write this again. The force of attraction will be proportional to the charges of those two bodies, and inversely proportional to the square of the distance between them. Now, when I put this sign of proportionality, that means that I have to, when I equate it, I'll have to introduce a constant. So therefore, the force of repulsion or attraction will be equal to Q1, Q2 times K divided by D squared. And this K is usually known as the Coulomb constant. Coulomb constant. Okay? Now, this, what I've written here is usually known as Coulomb's law. Coulomb's law, that the force of attraction or repulsion between two electrically charged bodies is usually proportional to the quantity of that charge between them, and it is inversely proportional to the distance, the square of the distance separating them. Now this K, the Coulomb constant, is usually approximately 9 times 10 raised to negative 9. Are we together? Tuko pamoja? You have the notes. I sent the notes in the morning, so if you want to follow what I'm saying, you can get the notes in the Google Classroom. The slide doesn't have a lot of notes, so I'll just be presenting equations, and then we'll be doing some questions. But if you want to understand my explanation, you'll find it in the notes that I sent. Now, we have talked about the field, the electric field. Now, how do we determine the strength, how strong that electric field is? Now, let us look at these two conducting plates that are parallel to each other and are connected to a voltage source V. Now, these conducting plates, because they are connected to a voltage source, there will be an electric field in the space between those two plates. Now, if those plates are close together, as we had seen in the diagram, this diagram, then these lines will be parallel to each other, meaning that the field of the electric field is strong when those two plates are close together. Okay? Now how do we determine the strength, the electric field strength? We will take the voltage in that circuit divided by the distance between those two conducting plates. That is where in this mahali ambapo the field is uniform. Kumbuka at the edges the field is not uniform, huku kando kando, but at the center the lines will be parallel to each other, meaning that the field is uniform. So in the place where the field is uniform, we can be able to determine the field strength of that electric field by taking the voltage in that circuit divided by the distance between those two conducting plates. Now, this electric field strength is also known as potential gradient. It is also known as potential gradient. So when you find a question, you might find you're told to calculate the field strength or the potential gradient. They all mean the same thing. Now, capacitance. We had introduced capacitors in our first classes, and we had talked about capacitance. Now, what is capacitance? Can anyone remind us what capacitance means? Tutajikumbusha. Go through those notes again so that we may remember. Now, for example, this diagram ambayo this previous diagram over here. Let's say this plate on the left is positively charged, and this plate on the right, no, this will be positively charged because of the direction of the battery, and this will be negatively charged. Now, because there is an electric field in between those two plates, then there will be charge. There will be charge in these conducting plates. This being a positively charged plate, and this is a negatively charged plate. Now we can be able to determine the value of capacitance given that there is a potential difference, a change in voltage in that circuit. And how do we calculate this? How do we obtain the value of capacitance? We can obtain the value of capacitance, the value of capacitance, or how much charge corresponds to the change in voltage by taking the charge in that capacitor divided by the voltage across that circuit. So we will have to first calculate. If you're told to find the capacitance, you will take the value of the charge divided by voltage. Now, in electric circuits, zile ambazo tumekuwa tukifanya, we have been talking about capacitors, and capacitors is just an electric component that adds the capacitance in a circuit. And when we talk about capacitors, we say that the unit of measurement is farads, usually denoted by F. Okay. Now, in the circuits that we have been drawing, we have been dealing with fixed capacitors, and that is the symbol. But we also have a variable capacitor. The same way we have a variable resistor, the same way we have a variable inductor. We also have a variable capacitor. Now, when we want to calculate, for example, you have a circuit and you have been told to calculate the charge being stored by that capacitor, you will take the current in that circuit in amperes and you multiply it by the time it takes to charge that circuit, or the time it takes to discharge that circuit in seconds. So the current in amperes times the time it takes in seconds. Now, the simplest form of a capacitor is two conducting plates with a dielectric. A capacitor must have a dielectric or an insulating material inside it, and the most common one is an air capacitor, ile ambayo kuna two conducting plates and the insulating material is air. But you also have different types of capacitors, and I've given that as an assignment for this week. We have paper capacitors, the dielectric is paper. We have mica, the insulating material in between the conducting plates is mica, and so on and so forth, aluminum foil. But the charge in all those types of capacitors will be given by the current times the time it takes to fill or to charge or discharge that capacitor. Now, there is an example here. You're told to determine the voltage or the potential difference across a 4 microfarad capacitor when it is charged with 5 millicoulombs. You're told to determine the value of capacitance, the voltage. You've been told to determine the voltage or the potential difference, given that we have the capacitance of that circuit is 4 microfarads. When it is charged with the charge in that circuit inakuwa charged na 5 millicoulomb. Remember that the unit of measurement of charge is coulomb. Please remind yourselves those electric quantities and the unit of measurement so that you don't usichanganyikie ukiona swali. Now, these units, this is in microfarads and this is in millicoulomb, so we have to change them to their fundamental unit. Kwa mfano, this microfarads, we have to change it to farads. So we will multiply this by 10 raised to power negative 6. This we will multiply by 10 raised to power negative 3. So that the capacitance will be 4 times 10 raised to power negative 6 farads, and the charge will be 5 times 10 raised to power negative 3 coulombs. Now, we have been told to find the potential difference, some of the voltage across that capacitor. Remember that charge, capacitance is given by the charge divided by the voltage. Capacitance is given by the charge divided by the voltage. We have the value of capacitance, we have the value of charge. So we've been told to find the voltage across the capacitor. Now, the value of capacitance is 4 times 10 raised to power negative 6 farads is equals to the value of charge, which is 5 times 10 raised to negative 3 coulombs, divided by the voltage across the capacitors. Therefore, the voltage across the capacitor is 5 times 10 raised to power negative 3 divided by 4 times 10 raised to power negative 6. This will give us a potential difference across that capacitor as Umepata ngapi? The potential difference or the voltage across that capacitor is 1250 volts. Now, are we together? Mmenyamaza sana na sijui kama tuko pamoja. If you don't understand anything, please ask. Usinyamaze. I want us on the same page. Is there a question up to that point? Yes? Sikusikii vizuri. Sawa sawa. Lakini formula umeshika. We can be able to find capacitance when you're given the value of charge and voltage. Now, tumepatiwa, so the value E5, unaweza ona calculator yangu. Okay, 5 times 10 raised to power negative 3 divided by 4 times 10 raised to negative 6. Get 1250. All I've done is I've put them in brackets to distinguish the 5 times 10 raised to power negative 3 and distinguish the other 4 times 10 raised to power negative 6. Kuna mtu mwingine ana swali? Sijui kama nimekujibu. Nimekujibu? Ndio answer. 1250 volts. Nione watu wangapi kwa hii class wamenyamaza bana. Rosemary, Miriam, James, Irene, are we together? Edwin, uko pamoja? Umepata 1250? Okay. Now, let us try this part B of the question, which says, no, another question. Okay. You're told to find the charge on a 50 picofarad, but I don't want you to find it. I don't want you to find it in farads. Picofarads is 10 raised to power negative 12, but I've changed it to farads. So find the charge on a 50 farad capacitor when the voltage applied to it is 2 kilovolts. Find the charge on a 50 farad capacitor when the voltage applied to it is 2 kilovolts. Applying this formula, that capacitance is given by charge divided by the potential difference or the voltage. You're told that find the charge Q, given that the value of the capacitor is 50 farads and the voltage applied across it is 2 kilovolts. Now capacitance is given by the charge divided by the voltage. Yeah? The capacitance, the value of the capacitor is 50 farads, is equals to the charge divided by the voltage, but the voltage is 2 kilovolts. So when you change it to volts, itakuwa 2 times 10 raised to power 3 ama 2 times 1000 to get 2000 volts. So divided by 2000 volts. Therefore the value of charge will be 50 times 2000 to give you 100,000 coulombs. We're dealing with charge. The unit of charge is coulombs. Sawa. Please let us remind, hizo units ni muhimu. Hiyo unit ni muhimu sana. Now let us attempt this question. We are told that a direct current of 4 amperes flows into a previously uncharged 20 microfarad capacitor for 3 milliseconds. Determine the voltage between the plates. You can write it down, I'll give you a minute. A direct current, a DC current of 4 amperes flows into a previously uncharged 20 microfarad capacitor for 3 milliseconds. Determine the potential difference or the voltage between the plates. Now, remember we said that the first thing I would want you to do every time you get a calculation question is to list down the quantities that you have been given. Tumeambia that a current I of 4 amperes flows into an uncharged 20 microfarad capacitor. Yeah? So the value of capacitance is 20 microfarads. And then you're told that it flows for the time it takes is 3 milliseconds. So you determine the voltage or the potential difference across the capacitor and the plates. Now remember that charge in a capacitor, when current flows through the plates is given by the current times the time it takes to charge or discharge that capacitor. When we look at our quantities over here, current is in amperes, therefore it is in its base unit, but the time is in milliseconds, so we have to change it to seconds. So this will be 3 times 10 raised to power negative 3, or you divide by 1000 to change it into seconds. Therefore the charge across that capacitor will be 4 times 3 times 10 raised to negative 3. So 4 times 3 times 10 raised to negative 3 to give us the value of charge as 0.012 coulombs. Now the question asks us to find the voltage or the potential difference across the plates. Remember that capacitance is given by the charge over the potential difference, the voltage. We have the charge and we have the value of capacitance. So, but our value of capacitance is in microfarads, so we have to change it to farads. So we will multiply by 10 raised to power 6 to change it to farads. So 20 times 10 raised to power 6, or we divide by 1,000,000. So 20, when you replace that in our equation, 20 times 10 raised to power 6 is equals to the value of charge ambayo umeobtain, which is 0.012 coulombs divided by the voltage, or what we are looking for, the potential difference. Therefore, the voltage will be 0.012 divided by 20 times 10 raised to negative 6. So 0.012 divided by 20 times 10 raised to negative 6 to give us a value for the potential difference across the plates as 600 volts. So are we together? Any question? Now, I want you to do this and give me the answer. We are still going to apply the same formulas, but now the question is asking you to find the time that it will take that capacitor to discharge. You're told that a 5 microfarad capacitor is charged so that the potential difference between the plates is 800 volts. Calculate how long the capacitor can provide an average discharge current of 2 milliamperes. So first thing, list down what you have. Then input or replace those values into the formulas, and then find the time that it will take the capacitor to give a discharge of 2 milliamperes. How long will it take? I also want to hear from the ladies, yeah? Irene, Miriam, Rosemary. Tuko pamoja leo ama watu wameingia tu wakazima simu na wakaendelea na shughuli zao? I want someone to give me an answer. What will be the value of time? Umepata ngapi? We will see shortly. I want someone else to give us a different answer for reference, ili tuone kama sisi wote tumepata the same answer. Anyone else? Kuna mtu mwingine amepata answer? Okay. I'm waiting for an answer. Kuna mtu amesema ningoje kidogo. Okay, acha tufanye. Now we were told that a 5 microfarad capacitor is charged so that the potential difference between the plates is 800 volts. So let's list down what we have. We have the value of capacitance as 5 microfarads, which is 5 times 10 raised to negative 6 farads. The voltage or the potential difference across the plate is 800. That capacitor has been charged. The potential difference between the plates is 800. We are told to calculate the time that capacitor will discharge at a constant rate of 2 milliamperes. So when you change this to its base unit, it equals 2 times 10 raised to negative 3 amperes, or 2 divided by 1000. Now, remember that capacitance is given by charge divided by voltage. Okay? Capacitance is given by charge divided by voltage. So when we make the charge, the constant Q will be equal to the capacitance times the voltage. Remember that also charge in a capacitor is given by the current times the time it takes. Okay? Now, using the quantities that we have been given, we can be able to find the charge using that first formula here kwanza. I don't know whether my work is clear. Yeah, using the first formula, then we can be able to find the charge across the capacitor. Remember the energy stored within, the charge in the capacitor. So Q will be equal to the capacitance, which is 5 times 10 raised to negative 6 farads, times the voltage across the plates, which is 800 volts. Therefore, the charge in that capacitor will be 5 times 10 raised to negative 6 multiplied by 800 volts to give us a charge of 4 times 10 raised to negative 3 coulombs. But remember, this charge can also be obtained by taking the current times the time. Now we have been told to find the time. How long will it take this charge about tumepata to discharge at a constant rate of 2 milliamperes, at a constant rate of 2 milliamperes. So 4 times 10 raised to negative 3 will be given by the current in that circuit, which is 2 times 10 raised to negative 3 amperes times the time it takes, and that is what we're interested in. Therefore, the time will be 4 times 10 raised to negative 3 divided by 2 times 10 raised to negative 3. So this will go. Kwa hivyo utabaki na 4 divided by 2 to give us 2 seconds. Therefore, this capacitor can provide an average discharge current of 2 milliamperes for only 2 seconds. That is the discharge rate of that capacitor. Kuna swali? Hii ya kwanza hapa. Umetumia ya pili. Hii tushafanya, sijui kama mlikuwa mmeona. Hata nirudi pale kwa slide. Hapa, when you're given capacitance, you can be able to, I mean, when you have the charge and you have the voltage, then you can be able to find the capacitance of that circuit. Kile sasa tumefanya kutoka kwa hii formula is we have taken Q as the subject. Tulikuwa tumepatiwa capacitance na tuko na voltage, then it is possible to find the charge. So all you have done is you said that Q is equals to CV. But also remember that Q is equals to the current times time. So, yes? No, tumetumia zote mbili. Sijui kama uliona. Ukiangalia katika question, the question was asking us to find the time that it will take to discharge that capacitor. We had been given the value of the capacitor as 5 microfarads, indeed. Tukapatiwa the voltage across the plate is 800 volts. And then we are told at what rate will it, what time will it take to discharge, to provide an average discharge of 2 milliamperes. Now, we don't have the charge, the value of Q, hatuna. And Q is usually given by the time, I mean the current times the time. But we do not have the time in this case, and that is what we are looking for. But remember that capacitance is also given by the charge divided by the voltage. Therefore, it is possible to find the charge by taking the capacitance times the voltage. Okay. We have made Q the subject from this formula capacitance. By making Q the subject, we can find the charge by taking the capacitance times the voltage. And that is what you've been given. We have the value of capacitance as 5 microfarads, and we have the value of voltage as 800 volts. Then the value of charge that we get, itakuwa 5 times 10 raised to negative 6 multiplied by 800 to give us the value of charge as 4 times 10 raised to negative 6 coulombs. Now, how long will it take for this 4 times 10 raised to negative 3 coulombs to discharge, so that we can get an average discharge current of 2 milliamperes. Therefore, now we use this second formula. So the charge will be given by the current times the time. We now have the value of charge as 4 times 10 raised to negative 3 time, is equals to the current, which we have been told is 2 milliamperes, which is 2 times 10 raised to negative 3 amperes, multiplied by the time it will take to discharge. And that is what we are interested in. Therefore, the time will be given by the charge divided by the current, to give us the time it will take to discharge that for these coulombs will be 2 seconds. Tumetumia these two, tumezitumia zote mbili, hizi formula zote mbili. Sawa sawa. Kuna swali lingine? Nitatumia tu. Acha tumalize hizi terms because we have to kwa sababu tumeanza tukichelewa, acha tusonge mbele kidogo, and then I will send some questions kama last week so that you can be able to attempt them at your own free time, ili kama kuna swali ukishindwa tutapitia. Sawa sawa. Now, electric flux density. Now, when we have this electric flux, the lines, easy lines passing through a specific area that is perpendicular to this direction. These lines of electric field are known as flux. When they pass through a particular point that is perpendicular to the direction of the flux, that is what we call electric flux density. And the electric flux density will therefore be given by the charge divided by that area. The charge of that field divided by the area of that ile mahali ambapo panapita. This, the electric flux density, is also known as charge density. Are we together? It is also known as charge density. And the unit of measurement for electric flux density is coulombs per meter squared. So. Now, let us look at something else known as permittivity. Permittivity is usually the ability of that insulating material. Remember that when you put an uncharged material or object in an electric field, then it will align itself kulingana na the charges. So when I place an uncharged material towards a positively charged particle, you'll find that the surface of that uncharged material will have negative charges so that it can attract each other. And those positive fields will attract the negative particles within that to the surface. Now, that ability of a material to realign its particles, its dipoles within itself so that it can ili iweze kuwa attracted ama repelled by the electric field is what we call permittivity. You'll find that there are materials whose atoms ama particles within them will realign themselves easily, na kuna zingine ambazo will resist. Like there will be different rates. There will be one that will align easily, there will be another that will not align easily kulingana na the electric field. Now, this permittivity is usually a constant, where we take it's a ratio, the ratio of the D, which was the electric flux density, divided by the electric field strength, to give us this constant, E naught. We'll call it E naught, and this is usually known as the constant. The permittivity of free space, the free space constant. The permittivity of free space. This is when we take when we establish an electric field in a vacuum, and then we take the ratio of the electric field density divided by the electric field strength. We will get the permittivity of free space, whose value is 8.85 or 8.9 times 10 raised to negative 12 F per meter. Are we together? When we have a capacitor, when we have two plates, conducting plates, and we establish an electric field in vacuum, or in this case air, then when we take the value of the density, charge density divided by the value of the electric field strength, we will get a constant. And this constant is known as the free space constant, or the permittivity of free space. And this is, its value is 8.85 times 10 raised to negative 12 F per meter, and this is a constant, it doesn't change. When we take, when we establish an electric field in a vacuum or in air. Now, when we establish an electric field, but we have an insulating material other than air, other than vacuum, in between those two conducting plates, then we establish, we modify that ratio to include something else here. This constant, we include another constant which is known as relative permittivity. You will find that these terms, when we talk about magnetism and electromagnetism and now electrostatics, they are similar. Ile wakati tutasoma mambo ya magnetism, we'll still be talking now, instead of permittivity, we'll be talking about permeability. It is how a material, in case of magnetism, is that how easily a material will gain magnetism. When you introduce it to a magnetic field, the measure of that magnetic field when then that is permeability in magnetism. But now in electrostatics, when you introduce a material to an electric field, the ability of that material to align to that magnetic field, those internal particles, the dipoles, is what we call permittivity. Now, when we have an insulating, when you don't have an insulating material in between those conducting plates, that is when you introduce, when you make when you produce an electric field in a vacuum or air, we get this constant, which is known as free space constant, the permittivity of free space. But now, if we have an insulating material, then we modify this constant of the ratio of the field density to that of the electric field strength to have this. We introduce this, and this is known as the relative permittivity. Now, this usually indicates how the insulating material, its property. It indicates the insulating power compared to that of vacuum, because this E naught R is a ratio. E naught R is a ratio of flux density, density of that material divided by the density of vacuum. Let's say this is vacuum and that of that material. So this is a unitless quantity, in a unit, because it is the flux density of that material divided by the flux density in vacuum. So it just shows the insulating power, the power of that insulating material that you have included between the conducting plates. So you'll find that this value will change kulingana with the type of material you use. If you use the rubber as the electric insulating material, that value will be different than when you use mica and so on and so forth. Now, when you take the product of these two, E naught times ER, the constant of free space times relative permittivity, you get something known as absolute permittivity, which is denoted by this E. Are we together? What we get is absolute permittivity. So, now let us attempt this question with those equations in mind. We're told that two parallel rectangular plates, each measuring 20 centimeters by 40 centimeters, carry an electric charge of 0.2 microcoulombs. Calculate the electric flux density. If the plates are 5 millimeters apart and the voltage between them is 0.25 kilovolts, determine the electric field strength. I'll give you a minute to write down that question so that we may be able to do it together. When you're ready, let me know. Okay, now let us do this together. Up to that point, kuna swali? Now, we are told that we have two plates, each parallel plates, each measuring 20 centimeter by 40 centimeter. And the charge that is carried between those two plates is 0.2 microcoulomb. So calculate the electric flux density. Now remember that D, electric flux density, is given by the charge divided by area. Remember that flux density is that flux, the length of flux, passing over a particular area that is perpendicular to that direction of that flux. Now in this case, with this, whatever we have been given so far is charge, the value of Q, but we don't have the value of A. But it is possible to calculate it because we have the dimensions of those rectangular plates. Now, the area of a rectangular cross-section is given by length times width. But you want the area in meters, so we have to change our dimensions to meters. So 20 centimeters will be 0.2 meters times 0.4 meters to give us that the area is 0.08 meters squared. Okay? Are we together? Now, so now the flux density, the electric flux density will therefore be given by the charge 0.2. Remember, it is microcoulomb, so we have to change it to coulombs. So 0.2 times 10 raised to negative 6 divided by, this is in coulombs, divided by the area, which is 0.08 meters squared. So when you take 0.2 times 10 raised to negative 6 divided by that, you'll get that the value of the charge density will be, the value of charge density, electric flux density, I mean, is 2.5 times 10 raised to negative 6 coulomb per meter squared. 2.5 times 10 raised to negative 6 coulomb per meter squared. Now the second part of the question is saying, if these plates are 5 millimeters apart, those plates are 5 millimeters apart, determine and the voltage between them. So the distance between them is 5 millimeters apart, and the voltage, the potential difference between them is 0.25 kilovolts. You're told to determine the electric field strength. Now remember that the electric field strength denoted by E is given by the voltage divided by the distance between the plates, the potential difference divided by the distance. We have these two quantities, but these two quantities we have to change them to their base quantity. So 5 millimeters to meters, it acquires 0.005 meters. You divide by 1,000. And for 0.25 kilovolts, you have to multiply by 1,000 to change it to volts to get that, to get to 50 volts. Therefore, the electric field strength will be that voltage, 250, divided by the distance between them in meters. This will give us that the field strength between those two plates, conducting plates, is 250 divided by 0.005. Therefore, the electric field strength will be 50,000 volts per meter. Are we together? Any question? Maswali? We are just applying the formulas that we have been talking about or we have been stating. These are just sample questions ambazo utapata katika mtihani ama in exams ama CAT. Now, I'll ask again, is there a question up to that point? Kila mtu ako sawa? If you're with me, please unmute and say that you're present. I really It's good to hear that you're with us. Now let us look at this question. You are told that the flux density between two plates separated by mica in this case is insulation, the electric, of relative permittivity of relative permittivity 5 is 2 microcoulomb per meter squared. Find the voltage gradient between the two plates. Find the voltage gradient between the two plates. Kuna mtu anaweza tujaribu hiyo aone kama atapata. Mica is the insulation between the two plates, kama rubber or air. So depending on the type of capacitor, you'll find that there are different dielectrics, some insulators put between the two conducting plates. We have paper, we have air, we have aluminum, foil, and so on and so forth. Now we are told that sorry, 2 microcoulomb per meter squared. That is the charge density, the flux density. Yes, the charge density. The amount of charge passing through a particular, the lines of flux passing through a particular point that is perpendicular to the direction of that flux is what we call flux density or charge density. Now, we're told that the flux density D, the flux density is 2 times 10 raised to negative 6 coulomb per meter squared. We had been given as 2 microcoulomb per meter squared, but I've changed it to coulomb per meter squared by multiplying it by 10 raised to negative 6. Between two plates which are separated by mica of relative permeability. Now the relative permeability of mica is 5. Remember, we have also that permittivity of free space, which we said that value is constant, and its value is 8.85 times 10 raised to negative 12 farad per meter. Now we're told to find the voltage between the two plates. Now, how do we find the voltage gradient? Yeah, the voltage. We're told to find the voltage, not the voltage. The voltage gradient. Remember that I had mentioned that the electric field strength is also known as voltage gradient. Do you remember? E. Voltage gradient is also the electric field strength. Are we together? Which is usually denoted by E. Sasa. Okay? So when you see a question asking you for voltage gradient, it's still the same thing as E, electric field strength. Now, remember we were told this is voltage gradient or potential gradient. Now, we have been given the value of flux density, we have been given the value of these constants, the permittivity, relative permittivity, and free space permittivity. Now, remember in that mahali ambapo tulikuwa tumesema that the permittivity is usually given by, it's a ratio of the flux density over the flux strength, the field strength. And if it is done in vacuum, in air, the value is usually a constant known as the free space constant. But if you introduce an insulation, an insulating material or a dielectric between the conducting plates, And this formula is modified so that we can include the relative permittivity, which indicates the value of, the insulating property of that material. Now, we have been told to find the value of E, the potential gradient, the electric field strength. We have the value of flux density as 2 times 10 raised to negative 6 coulomb per meter squared. So 2 times 10 raised to negative 6 divided by E, the potential gradient, is equal to this constant of free space, which is 8.85 times 10 raised to negative 12 multiplied by the relative permittivity, and we are told that the relative permittivity of that insulating material mica is 5. Therefore, E, the potential gradient, will be given by 2 times 10 raised to negative 6 divided by 8.85 times 10 raised to negative 12 multiplied by 5. So the value of potential gradient, the field strength, will be 2 times 10 raised to negative 6 divided by 8.85 times 10 raised to negative 12 multiplied by 5, to give us that the value of the strength, the field strength, is 45,197.74. Kuna mtu amepata hiyo? Kuna mtu amepata? Anyone? Volt per meter. Always remember to include your units. What we have done is we have used this formula up. This constant d over E is equals to E naught times ER. We have D, the flux density, we have E, which is usually a value constant 8.85 times 10 raised to negative 12 farad per meter, and we have the relative permittivity, which we have been given for mica is 5. So what we don't have is a potential gradient, the electric field strength. So what we've done is we've made E the subject. By making E the subject, we have divided this value of the density divided by the values of these two constants to give us that the field strength value yake ni 45,197.74 volt per meter. Any question up to that point? Kuna mtu amepata a different answer? I hope people are attempting these questions, because these are the questions you will find in the exam. Naona watu wananyamaza na waulizi swali lolote. So I'm assuming either you're not with me ama you're understanding completely. Unajua mwalimu akiuliza swali and there is silence, either kila mtu ameelewa ama hakuna mtu ameshika chochote. So if there is any question, let me know. Kama kuna mahali hujaelewa, also let me know so that I may assist you. So that when I send a cut this week or next week, you hutapotee. swali? So everyone who is in this class has gotten the value of the field strength to be 45,000. Kila mtu amepata 45,000. Napata value ngapi? What do you get? Even when you do you put this times 10 raised to something ama iko hivyo tu. Now try including brackets in your values. .3. Let us do it together. Always make sure ukifanya hii mambo times 10 raised to negative something, make sure all those values utumie brackets so that you're able to separate which is which. So 2 times 10 raised to negative 6 divided by 8 mi hupenda kutumia hiyo kwa sababu hii ni mi naona mahali na whatever value I'm entering. Hiyo nyingine sipendi kuitumia because it's very easy to make mistakes. Wacha ni ile tu uko comfortable nayo. That is what you get at 5,197.74 volt per meter, ama 45.2 kilovolt per meter. At your own time, you'll do that. So. Now, the final thing I want to talk about now is how do you find the capacitance of a parallel plate capacitor? Remember that what we have been talking about so far is two conducting plates that are parallel to each other. And that is essentially a parallel plate capacitor. When you have two plates ambazo ziko connected that are parallel, and they have an insulating material in between them, then what you have there is a parallel plate capacitor. And then you connect that capacitor to a circuit. So this is the area, this is the distance between those two plates, and this is area A, and then this is the electric, the insulation. You will find the insulating material will be in between those plates. Now, when you do an experiment of a parallel plate capacitor, you find that the capacitance C is usually proportional to the area of the plate and inversely proportional to D, the distance between those two plates. And it depends on the nature of the dielectric. Remember, when you have different insulating materials, then the values of the permittivity, the relative permittivity will differ. So the relative permittivity of air, the relative permittivity of rubber, mica are all different. Therefore, the capacitance of that capacitor, a parallel plate capacitor, will be dependent on the area, will be proportional to the area, directly proportional to the area, and inversely proportional to the distance, and also depends on these two values. The nature of the electric, which when you quantify it as values, is this constant, the free space constant, and the relative permittivity of that material. Now, when you are calculating the capacitance, itakuwa E naught times ER times the area divided by the distance, and the unit of the capacitance is farads. Are we together? The capacitance of a parallel plate, two parallel plates, only two plates, is the free space constant times the relative permittivity times the area of those plates divided by the distance between those two plates. Okay? Now, if I have multiple plates, I can arrange multiple plates. They're still in parallel, but I want to increase the value of capacitance, so I overlay them on top of each other. Ni kama nimezimesh pamoja. What I'm essentially doing is I'm increasing the value of capacitance by increasing the number of plates in my capacitor. Now, the capacitance of a multi-plate, when you have more than one plate, will be given by, it is still directly proportional. I mean, it depends on the type of insulating material, times the area, but now we have to include the number of plates. And how do we find the number of plates? It is the n, which is the total number of plates, minus 1 to give you the number of capacitors. The number of capacitors in a multi-plate capacitor is n, which is the total number of plates, minus 1. So if I have 20 plates, then the number of capacitors will be 19. If I have 30 plates, then the number of capacitors in that capacitor is 29. So the capacitance of that capacitor will be given by this formula. For only 2 plates, then itakuwa this formula. Sawa sawa. Are we together? Okay. Naona watu wananyamaza. Tutapatana kwa mtihani. We will see each other in the exam. Now let us try this example. I'll send the example so you can try. You just use those formulas too. Ama tuvifanye. Do we do it now, or we do it? I send it to you and you try it. Okay, I'll send it to you so that you can attempt it. What I want us to do on Friday is we will see how the effect of arranging capacitors in series and capacitors in parallel. Tutaingia katika mambo ya circuits tena. How to find when you have capacitors connected in series and you have capacitors connected in parallel, how that affects their capacitance, so that we can be able to finally find the energy stored in that capacitor. So, okay, now is there a question?